For quantum physics, you are basically just talking about why is it that you can consider that certain particles can behave as waves? Why is it that certain waves can behave as particles? That is what your quantum physics is really about, okay? So one of the first things that you will learn in quantum physics is photoelectric emission. Now, for photoelectric emission, what we will tell you is that if you have a piece of metal and then you expose it to electromagnetic radiation, EM radiation, provided it has a certain frequency, provided it is of sufficiently high frequency, you will notice that your metal surface will emit electron. Okay, that is what photoelectric emission is. Emission of electrons from a metal surface when it's exposed to EM radiation of sufficiently high frequency. Your EM radiation here can be in the form of ultraviolet light, microwaves, visible light, gamma rays, so on and so forth. Those are your EM radiation. So provided the EM radiation is of sufficiently high frequency, you will get emission of electrons. Now, when people want to explain photoelectric emission, they found out that they cannot really explain photoelectric emission if you consider EM radiation as wave. Previously, all this while you have been taught to consider EM radiation as a wave, isn't it? So the thing is that if you continue assuming that EM radiation is a wave, you will not be able to explain photoelectric emission. You will find out later on you can only explain photoelectric emission if you consider EM radiation as particle instead. Okay. Now, what they found out from your photoelectric emission, from the actual case of photoelectric emission, the actual observations were these four. There is actually a minimum frequency for emission of photoelectrons, which is the electrons that get emitted during photoelectric emission. And then there's instantaneous emission of the electrons. And then the maximum K of the electrons depends on frequency. However, the maximum K of the electrons does not depend on intensity. These were the main observations that they found when they were looking at the observation. These are the main observations that they, something. Okay, these were the main observations that they saw when they studying photoelectric emission. These four observations is already inside your notes. I think it's either page 3 or 4 or 2. You need to remember these four. Okay, these are very important to remember. What are the observations of photoelectric emission? Okay, now these four observations for actual photoelectric emissions, they cannot be explained if you assume that EM radiation is a wave. Because if you assume EM radiation as a wave, you would have expected this kind of observation instead. You would have expected that your electrons will be emitted, there is emission regardless of your frequency. And then as long as there is continuous exposure to your EM radiation, emission will eventually happen. But that one is not clearly what has happened here. You see that when the emission happens, emission will happen instantaneously, not after a period of time. And then after that, you also find out that no matter how long that you expose the metal surface to, if the frequency is a very low value, is below a certain minimum value, no matter how long you expose it, no emission whatsoever. Okay, so that is what you have expected if you have EM radiation as a wave, because here the main assumption is that they assume that your electrons inside your metal surface is continuing to accumulate energy from the wave. So as the EM wave hits your electron, the energy absorbed by the electron keeps building up until it achieves sufficient energy to escape. But somehow it did not happen. Your actual observations is not supporting that. Okay. Then after that, they also found if you assume that EM radiation is a wave, you would have thought that if intensity increase, if under most cases, you have thought that if intensity increase or frequency increase, that means more energy, right? So more energy means more Ke of the electrons that are emitted, right? That is what you have thought here. If you're talking about the maximum kinetic energy of electrons that are emitted from photoelectric emission, if you have increased frequency, obviously your max Ke of your electrons will be increasing. If you have higher intensity, you will obviously have a higher max Ke of electrons. But what you found from the actual observation was that the Ke actually just depends on frequency, higher frequency, higher Ke. But then the intensity, if you increase the intensity, the max Ke actually did not increase at all. So there's some contradiction here. Okay, so to explain all these four observations, your EM radiation as a wave cannot explain all of them. Okay, so the only way to be able to explain this observation is if you assume that your EM radiation consists of particles rather than considering that it is a wave like this. It consists of particles, the green colored circles here. All right, so if you consider your EM radiation as particles, what do you actually consider here? You consider the EM radiation as particles called photons. Now, photons are actually packets of energy. All right, photons, you can think of them as simply packets of energy. All right, and when you're talking about photons being packets of energy, how much energy does a photon contain is given by this equation where it is E equals to hf. E is energy, h is your Planck constant, and then after that f is the frequency of your EM radiation. Okay, so let me just write something here. Okay, now then after that, what you needed to know was that if your electrons were to escape from the metal surface, it needs a certain minimum energy to be able to escape from the surface. So if you don't consider that this is your surface of your metal and then the electrons are here, if your electrons wants to escape from the surface, it has to overcome the other attractive forces between the other atoms or other electrons inside the metal surface itself. So to escape, you need energy. And to be able to escape here, you need to have a certain minimum energy to be able to escape. So the idea here is that if you have a certain minimum energy to escape, that means you need to have a certain minimum frequency of EM radiation, a certain minimum frequency of your photon. So that one will kind of explain these two. There is a certain minimum frequency required for the emission of electrons because you need a certain minimum energy in the first place. And this one will explain the instantaneous emission part. Why is it that as long as you have minimum energy of your photon, your electrons can be emitted instantaneously? Now, I think this part here, yeah. The other part here that I need to talk about is this. Second part here, when electrons absorb or interact with a photon, you can only do so one at a time. Meaning to say, if this one was your electron, and then you have one photon, this is not proton, this is photon. The electron absorbs the photon, and say this one has 100 joules of energy. So your electron will gain 100 joules of energy. But say for the energy for your electron to escape is say energy to escape is say 200 joules. Okay, so let's just say for example right now you have a surface with an electron. The energy required for this electron to escape is 200 joules. Your electron is absorbing a photon that has an energy worth 100 joules. So now if your electron absorbs a photon that has an energy worth 100 joules right now, it does not have that energy required to escape. Okay, but what happens to this electron here that has absorbed the 100 joules of energy? The energy that the electron has absorbed needs to be dissipated completely before it will absorb another photon. You cannot say that in this case here, I have two photons that are worth 100 joules. Why not I just say that the electron absorbs the first photon, so it get 100 joules. Then the electron continues to absorb another photon, so I get another 100 joules, so that I get enough energy to escape. It doesn't work that way. Okay, when your electrons absorb your photons, it can only do so one at a time. Okay, it cannot keep on absorbing photons continuously and then have its energy accumulate. Okay, whatever it has absorbed, that energy, either they use it to escape or either they completely dissipate it off by moving even faster within the metal surface before it can even interact with another photon. Okay, so that is the key main thing here. All right, actually this one will explain more on the part why you have instantaneous emission, because here it's telling you that there's no accumulation of energy. It's just that as long as you have enough energy, it escapes. If you do not have enough energy, then it will never escape. And it will not keep on storing the energy so that it's enough to escape. Okay. So yeah, what I will say here is that if you're talking about this point, electrons need a minimum energy to be able to escape the metal surface. So since there's minimum energy, there is minimum frequency. That will explain this part number 1 here. And then when electrons absorb and interact with a photon, they can only do so one at a time. The energy absorbed from the photon must be completely dissipated before the electron will accept another photon. This one explains the instantaneous emission part. Okay, because this one tells you that you do not have accumulation of energy. So if you do not have accumulation of energy, this tells you that as long as you have minimum energy, it will straight away escape. But if you do not have the energy, nothing will happen. It will need to dissipate off that energy before it will interact with another. Okay, so that part is this. Now then the other part here is that for energy or photon that is absorbed, part of the energy is used for the electron to escape the metal surface, while the remaining part is converted to Ke. Okay, so the idea here would be that the greater the photon energy, the greater the balance of energy that will be converted to Ke here. So the example would be what I've written there in this little diagram here. So say for example, I have the electrons here, and I tell you the minimum energy to escape is 20 joules. Okay, and now I have these 3 photons, 1, 2, 3, each of different energy. If this one is 100 joules and is absorbed by the electron, 20 joules is used for the electron to escape. The balance of 80 joules is converted to Ke. Likewise, if I have 200 joules of energy here that is absorbed by the electron, 20 joules has been used by the electron to escape, while the balance has been converted to Ke. So same thing again for the 300 joules photon. 300 joules is absorbed by the electron, 20 joules is used to escape, but the remaining 280 joules will be converted to Ke. So here you will see that if in the first place the energy of the photon is high, meaning to say it has higher frequency, you have more energy that is converted to Ke. So you have max Ke being dependent on frequency here. So this will tie to this. Okay. Now the part where you want to explain why Ke, maximum Ke does not depend on intensity, you would have to refer back to the definition of intensity. Intensity in your AS physics, we told you it is energy per unit time per unit area, right? So when you're talking about energy here, energy is talking about the total energy of your photons. And now the total energy of your photons, you know that it consists of packets of energy, right? There are a number of photons, each with their own energy. So if you want to find the total energy here, you can actually say that the energy of your EM radiation is actually the number of photons you have multiplied by the energy of a photon. So that's why it's N times E here, divided by T, divided by area. Okay, so this one is intensity here, which we define for you in AS physics. So say for example right now, we tell you you increase your intensity of your EM radiation, but we maintain frequency constant. Okay, if we maintain frequency constant and area constant, your intensity will actually be proportional to N over T. Okay, so what is the effect of having frequency constant here? Because you see just now I told you that frequency This is separate column. This part here. I told you the energy of a photon is dependent on frequency because E is equals to hf. So if I told you that F is maintained constant, that means E is constant. The energy of the photon is constant. E is constant, and then I assume area is constant too. You will see that intensity is actually proportional to N over T. Number of photons per unit time. Okay. So I is proportional to number of photons per unit time, N over T. This one will tell you that if you have increased intensity, you actually have more photons per unit time. There are more photons that are incident on your metal surface. So this in turn leads to more electrons emission also. Okay, so you have more photons per unit time of incident on your metal surface. That means you have more of them being absorbed by the electrons. You're going to have more electrons emitted per unit time. Okay, but in the case here, for the electrons that you emit, the electrons themselves will not have higher max Ke because the energy of the photon that you absorb in the first place here did not increase, as I mentioned here. Okay, so that's the reason why we will tell you that the maximum Ke of your electrons emitted actually does not depend on intensity. What it does cause is more electron emission, that's all. But it doesn't cause the maximum Ke of your electrons to be higher because what your electron got in the first place from the photon, the energy that your electron got from the first place from the photon did not increase, it did not change. So you don't expect your max Ke to be any larger. Okay, so this is photoelectric emission. Okay, it is important that you memorize these 4 observations. They will always ask you these 4 observations. The question, typical question will be, they will ask you, what is the observation of photoelectric emission that supports EM radiation as a particle? Then you have to say these 4 observations. Likewise, they can also word the question in such a way that when they ask you, what is the observation of photoelectric emission that does not support EM radiation as a wave? You will also reproduce these 4 observations. The ones that are here, you do not need to memorize. This is just for your further understanding, that's all. But this one here, you definitely need to memorize. Okay, so that one is for photoelectric emission. Then I think I go on to your next one, more on the calculation part. So let me just clear off everything. Okay, now if you go to the next little picture that I sent to your chat group, this is little one here, right? Now, as I mentioned to you just now, you need whatever your electron absorbs, the electron will absorb the energy of your photon. Part of the energy of your photon will be used to escape from the metal. Part of it will be used to be your Ke, right? I mentioned something like that. So say for example, here I have a case of 2 photons, one is 100 joules, one is 150 joules. Your electron here can absorb the photon of 100 joules. And if I say for you the energy required to remove the electron is 100 joules, this electron absorbs this 100 joules of energy. It will be able to escape, but there's no Ke. It just goes to the surface and then gets absorbed back, that's all. But when I'm talking about, say, this 150 joules of photon, and the energy to escape is 100 joules, 100 joules will be used to escape. Oh, okay, wait. My screen is frozen, is it? Okay, can you see this diagram now? Because I'm not opening from PDF, I'm opening from individual photo screen. Okay, right, so let's just look at this one here. So you all can see this one now. Okay, so let me just reiterate what I just mentioned to you. For your case that I mentioned to you, your electron will interact with a photon. It will absorb the energy of your photon. Part of the energy of your photon goes into removing the electron from the surface. The balance will be converted to Ke. So like in the case of this thing here, 100 joule comes in, but 100 joules are needed to remove the electron from the metal surface. What happens here is that this whole 100 joules has been used to remove the electron only, but there's nothing remaining for Ke. But if say I have a photon with 150 joules, like this one here, 100 joules will be used to remove the electron, but the remaining 50 joules will be used out as Ke. Okay, so that part is okay. Now, if I want to talk about this thing in general, for example, it is correct to say that energy of photon that has been absorbed by electron is equals to the work done to remove the electron from the metal surface plus Ke of electron, right? Because the idea here is that whatever photon energy you have, part of it is used to remove electron from the metal surface, part of it is converted as Ke of electron. Okay, so this one here is in general what happens. Okay, but the thing here is this, you see, if I talk to you about, say, electrons that are not at the surface of the metal, not near the surface of the metal, I talk about electrons that are, say, further deeper down in the surface of the metal. This part here would be, if I have, say, an electron here, the one in the third layer here, and I want to talk to you about the energy that will be required to remove the electron. If I talk to you about this one here, the third electron here, at the third layer here, since this electron is deeper below the metal surface, what can I say about the energy required to remove the electron? You see, because this one here is deeper below the metal surface, if you want to bring it up all to the surface, it will collide with the other electrons or the other atoms. It will have to overcome even more attractive forces, right, as it is brought up to the surface. What you can say is that for electrons that are deeper below the metal surface, more energy is required to remove from metal because more work needs to be done. Okay, so for the electrons that are at the metal surface, when you're talking about the energy that is required to remove them, they don't all have the same values. It depends on where the electrons are. If you're talking about at the metal surface, the idea is that it tends to use up less energy to remove because they are just at the surface. But if say you have electrons that are deeper below the metal surface, you actually need to have more energy to remove them because you have to overcome the attractive forces of all the other atoms and electrons here. You have to push it up all the way to the surface and so on and so forth, right? So deeper below the metal surface, you have to have more energy required. Okay, so if you have more energy required to remove electron from the metal surface, where the deeper, I think let me just write this here. Further below the metal surface, yeah. If I talk to you about this, further below metal surface, you say further below metal surface, you need more energy to remove electron from the metal surface because more work needs to be done. But at the same time, this also tells you one thing, right? There will be less energy as Ke, right? There'll be less energy as Ke, isn't it? So if you're talking about electrons below the metal surface, energy required to remove electron is higher, and as a result, you have less available as Ke. But for this entire layer itself, this equation is still valid. whatever energy or photon you have, part of it is used as work done to remove electron from the metal surface, part of it is converted to Ke. This is a general form of the equation representing what happens here. But if you talk about specifically only electrons at the metal surface, you could say this: the electrons at the metal surface actually need the least work to remove. Okay, and because they need the least work to remove, you're gonna get the max Ke of your electrons. If you're ever gonna get any maximum Ke of electrons, it's usually only at the metal surface, for electrons at the metal surface, because they use up the least energy to be removed in the first place. For electrons that are deep below the metal surface, your Ke will not be maximum. It will actually be less, because in the first place you have to do more work to bring it to the surface and to remove it. Okay, so specifically only at the electron, for the electrons at the metal surface, this equation can be modified to this. Okay, and it's from this equation that you get this. This is what you call as Einstein's photoelectric equation, which tells you a few quantities, how you calculate the Ke maximum of the electrons emitted, and what is the actual energy that you need in order to remove electron from the metal surface. Wait, let me just see what can I rub off here. This is the thing I can rub off. Okay, so this one is Einstein's photoelectric equation is modified from this. As I mentioned to you, energy of a photon is Hf. Okay, now minimum work to remove electron from a metal surface is denoted by this symbol phi. It is called your work function energy, minimum energy of photon to remove electron from metal surface. Okay, and your Ke max is just your Ke max. Okay, and then this equation can be further changed into another form. If this one is in terms of frequency, you can change it to in terms of wavelength. Because you know that V is equals to F lambda. So the V here is speed of light. I changed it to a different variable called C. Frequency itself is C over lambda. So if this one I sub inside here, you get Hc over lambda. All right. So that part is okay. So you get two forms. It depends on the question context, whether you're dealing with frequency. If you're dealing with frequency, you use this. If you're dealing with wavelength, you use this. But just know that these two is normally dealing with electrons at the metal surface. They are not talking for electrons that are much deeper below the surface. It's only applicable for electrons that are at the metal surface, meaning to say somewhere around here. That's all. Okay. So then after that is from this little equation here that you need to talk about a few things. Now, these equations that you have here, if you want to find out certain things like the minimum frequency for photoelectric emission, the maximum wavelength for photoelectric emission, you can find it out from this equation. Remember just now in the previous screenshot, I told you that there is minimum frequency for emission of photoelectrons because there is a minimum energy required for electrons to be able to escape. So the thing here is that what is that minimum frequency? The minimum frequency is what we call as threshold frequency F0. Okay, so I told you just now, for emission electrons to occur from your metal surface when exposed to EM radiation, there has to be a minimum frequency of your electron. Sorry, there has to be a minimum frequency of your photon. Okay, and what is that minimum frequency? We call it as threshold frequency F0. Now, the threshold frequency, at threshold frequency itself, what we will tell you is that your photon has just sufficient energy to remove electrons from the metal surface. There is no balance remaining for your Ke. It's actually referring to this case here. This is already at threshold frequency case. Okay, at threshold frequency case, whatever energy or photon you have is just enough for your electron to be removed from the metal surface, but there's no longer any energy remaining for the Ke. So if that's the case, you look at this equation here, that will mean, yeah, I have it here already. HF is equals to 5 plus KE max, right? If I consider that at threshold frequency, KE is 0, this one becomes 0, this one becomes F naught, this equation becomes this. So HF naught is actually equals to 5, okay? Now, if I want to go and change it, I don't want to talk about frequency required for photoelectric emission, but this time I want to talk about wavelength required for photoelectric emission. I will talk about the concept of threshold wavelength. What is the wavelength required for emission of electron from the metal surface? Now, in the case of you talking about wavelength, it is not minimum wavelength, it is maximum wavelength to cause emission of the electrons, because you see from here, V is equals to F lambda, F is equals to C over lambda, C being constant would mean that F is inversely proportional to lambda. They have an inverse relation. So if you have frequency being minimum, you're definitely going to have lambda being maximum, okay? So here, that's why we say to you, when you're talking about threshold wavelength, it is the maximum wavelength to cause emission. Any wavelength more than that maximum value, you will not get emission. You need to have wavelength less than this value to cause emission, okay? So at threshold wavelength itself, the same things also apply. The energy of your photon is just enough for your electrons to escape, but there's none remaining to be converted to Ke. So your Ke max is 0. So from this equation here, your lambda becomes lambda naught, your Ke max becomes 0, you get this, okay? So when it comes to finding the work function energy of a particular metal surface, what is the minimum energy of photon required to remove electron from metal surface? These two equations can be used. It's actually derived from this in the first place. Okay, so that part should be fine. Right, so far so good with this. Then I move on to another separate diagram, which is this one. So let me clear off that one. So like just now I told you, for Einstein's photoelectric equation, that one is only applied for electrons at the metal surface. And it gives you HF equals to 5 plus Ke max. It gives you HC over lambda equals to 5 plus Ke max, right? So there are cases where that equation can be used to plot a graph. Say for example, right now I want to plot a graph of Ke max versus F versus frequency. I rearrange this equation here. Wait, let me see. I think I didn't share the photo there. Right, this one I think you guys can see now, right? This is the new screen share. All right. Wait, let me see. Let me check. Yeah. Okay. Just now, as I mentioned to you, your Einstein photoelectric equation is either this one or this one. This one is in terms of frequency. This one is in terms of wavelength. If you want to plot graphs out of it, you can. You can say, for example, plot a graph of Ke max versus frequency here. This one, you will rearrange it in the form of y equals to mx plus c. You notice that you're getting a straight line graph with a negative y-intercept. Okay, so your gradient here is actually equals to Planck constant. Planck constant is a constant. You don't need to know so much about what it is. It's just a value there. It's called Planck constant. Okay, so for this case here, h is equals to gradient. All right, and your work function is your y-intercept. Okay, so y-intercept is your work function, and then this part here, the x-intercept is actually your threshold frequency. Remember just now I told you at F naught, Ke max is 0, is this part here, because here is 0. So the frequency at which your Ke max is 0 is F naught. Okay, so this part is okay. If you look at the equation Hc over lambda equals to 5 plus Ke max, and you want to plot a graph of Ke max versus 1 over lambda, you want to make it into an equation of a straight line, you rearrange it to become this form, then you get this. All right. Now in this case here, some things still remain. Your y-intercept is still gonna be your work function, but your gradient now is actually going to be HC. Okay, so there's a difference here. Gradient here is equals to HC. And then the other thing here also I need to mention is at threshold wavelength, again your KE max is 0, right? So you look at this part here, this one is 1 over lambda, so this value here must be 1 over lambda naught. Okay, so a lot of your questions that deal with the calculation and the graph, you need to know what to look for and what certain quantities represent here is deduced from your photoelectric equation expression in the first place. Okay,